FPGA design process, both what is the design flow of FPGA and how it is industrial use and applications of FPGA. So in IC designs, it is divided into two kinds of designs basically. Now in industrial perspective, it is divided into two, like ASIC design and FPGA design. So as it is name suggested, FPGA is field programmable gate array. It's a type of IC integrated circuit that are based around a matrix of CLBs and programmable logics, as you saw in my PPTs in slide, CLBs, IOBs, and all PLL, DSPs, MEMs, all are connected memories. Everything is connected together, and this forms FPGA chip basically. And first, it is invented by Ross Freeman and Burnett in 1985. So, why it is in demand? What is the scope of FPGA? Further in our slides to discuss. First of all, the gate array is in this FPGA word, like a field programmable gate array. Gate array is a regular or a systematic arrangement of logic gates. And now gates are million gates also. It's a number of so many gates we are connected. And this is a gate array structure that is in my slide I'm showing. This is the basic gate array structure, and this is the nascent and small structure that is connected in this FPGA full chip, and all these are the IOBs, input output circuits. When we connect all these circuits and these gate logics, then it is formed in FPGA circuitry. Now, along with FPGA, there is a demand of ASIC also, that is application specific integrated circuit. So application specific circuits are also important, but in FPGA designs, that is reprogrammable. That is, we can in between our designs we can change it whenever it is required, according to power, area estimation. We can change our designs in FPGA ICs. But similarly, if we are using ASIC designs, that is application specific, some that is designed for some specific applications. So we can't change it in between our design process. So that is the complexity of ASIC designs. Although it is also very beneficial in industry purpose, but because of it is application specific, we are so many constraint we are facing in this. So in FPGA is nowadays more highlighted, and FPGA designs are mostly used in defense, radar systems, all other applications that we can see in our slides also. This is the FPGA design flow. Like any question in any slide, you can please continue with slides also. Anyone? Am I audible?
Yes, madam, you're audible.
No one answer actually. If any question regarding FPGA introduction, then you can please ask. Okay, now we move to FPGA design flow. Whatever is showing in this slide, this is the basic design process of FPGA. Similarly, ASIC also have some design flow, how we can take a design from our customer side, and how can we implement it, how can what all process is going through in this design. That is I'm showing in my slide. This is the design flow. In first step, we are we are deciding, like source file, what is the design we want from customer sides we are getting. So that design is that design we are preparing in first step. After that, when all the gate in this source file that contain like our basic design structure, like coding part of our design. Like I want to design full adder, So what all gates are using in full adder, that particular codes and their coding part is completed in this first step. After that, we move to synthesis process. So one file is generated, that is comes under synthesis process, and in synthesis process, gate level netlist we generate. So in synthesis process, that gate level netlist generated, whatever in first step we are completed code part, that netlist is generated in synthesis process. And then we move to implementation process. In implementation process, there are three steps. First is translation, then mapping, and then place and route. Translation is like a number of netlist files we generated in that part, that we merge along with. So because like full header I am creating, so what all gates, and in that gates, what all circuits I'm preparing, what all codes of particular gates I'm deciding, that all are merged in that netlist. And there in netlist, all the specification of our gates, and what all voltages, what all input outputs we are using, that is specified in netlist. So that all merged part is involved in translation part, that I am not adding these 3 points: translation, mapping, and placement and route. um, these three things we are doing in implementation part. So we are adding that merged file. And then in mapping, as you saw in this FPGA chip, that CLBs and IOBs are connected. So in mapping part, what all netlist are connected, that we are adding in our chips, and then these IOBs and CLBs we are connected, mapped together in this mapping part. And then we move to place and route system, that in place and route we are checking basically area and power estimation about whatever the circuit we are using for our design, that is feasible for our chip, on that is feasible for our design. Accordingly we are place and route, placement, as name is suggested, like we are placing all the IOBs, CLBs in that circuit. So in placement and routing, we are checking that area estimation, their power estimation, and complete it like that. For after completing this implementation process, we are moved to bit stream generation. That is the final stage basically. In software side, that is final stage. So in bit stream generation, whatever the whatever the that is bit stream is like a file only. Whatever the full circuit is prepared, design is prepared, that we want to deploy in FPGA board, that one file is created, that is called bit stream file. That bit stream file is readable only for FPGA. What FPGA we are using, like we in initial stage we choose the FPGA kit, like Vertex, Hypex, Ipex, what all we are FPGA board we are using. That bit stream file should be readable according to our board. So we are using in bit stream file is most important. Final bit stream is generated, then only we can deploy it in for testing purpose in FPGA kit. So this is all the process of FPGA design flow. So move to further, as I also discussed in initial in my PPT, that what all differences in FPGA. Now we highlighted this comparison. So in FPGA based design, that is more that is more flexible comparatively to ASIC designs, and the hardware is already available for FPGA, because it is fully hardware based. And so NRE cost, like recursion cost of for market, its cost is less. But but in ASIC their initial cost is very high, because in ASIC designs we have to go to more steps, like verification, and then after verification we go for like photolithic synthesis and photolithic process, and all these things when we deploy our designs in IC. Basically, fabrication process is more in ASIC design. So that's why it is more complex, and it takes more money in initial stage. After when we complete one design, then after it is less costly when we design more products. Like I design some Bluetooth or some system, Bluetooth system, but initially it takes more cost. But after completing one design, if we go to move to plant based design, like more products we want, then it takes very less cost in ASIC designs. So this is the advantage and comparison of FPGA comparatively to ASICs. And like standard array designs, and hence most time hardware goes to unused in FPGA. So this is the disadvantages of FPGA. Like it is based on hardware designs, so hardware is many time not used, and it is wastage. So that is the basic disadvantage of FPGA design. Now move to application process. Like in FPGA designs, mm, FPGA designs, we are using most of the FPGA designs in defense part. Why? Because in defense, so many circuits in between completion of that circuit, or in between completion of our design, when we deploy it in our boards, many times we need to change the parameters. So that is mostly used in defense part. In between we can change. It is not a particular one specific application based. So ASIC designs are not used in defense applications. And in FPGA, it is because it contains more and more logics comparatively ASIC designs, because ASIC is using only one specific application. So um, cost is speed is very slow in FPGA design comparatively to ASIC, because application is only one. So we can extend our speed and area and power we can use in ASIC designs. Low power designs in industrial purpose, in low power designs we are mostly using ASIC designs. So this is the advantages and disadvantages of ASIC and FPGA designs. Um, Now, as from starting, I am talking about applications of FPGA. So in communication, avionics, missiles, secure systems, high-end radars, and space applications, we are using FPGA designs only. And in portable electronics, software defined radios, like in modulation, demodulation, software-based designs, we are using FPGA designs only. DSPs, we are using VLDRDO, all are using FPGA designs only. High resolution video, audio processing, automotive informatics, we are using FPGA designs. In switches, routers, encoders, decoders, servers, data center securities, we are using FPGA design. Like in digital cameras, set-up box, multifunction printers, digital display, we are using FPGA designs. So nowadays, FPGA is more used in like in electronics devices. But ASIC also is important, and it is also used in fabrication part. We are using ASIC designs. But yeah, it takes longer time to prepare. So this is the differences. So this is my slides. Anyone wants to any query? Anyone? Yes,
Can you go
yes.
to the previous slide, ma'am, in the second slide, slide number 2?
Yeah.
So you are saying this IOB and CLBs, right? So what is the
Mhm.
exactly concept, like IOB and CLBs? Like, will it be circuit is built? I mean, all the gates will be there, or what will be there, ma'am, in this one?
Yeah, yeah. CLB is complex logic blocks. These are also logic blocks, basically, that is already we found in FPGA kits, like Xilinx, whatever, like in Vertex, we are using Vertex. What all board we are taking, that is already defined in that boards.
So So how we will map, like there will be a tool that will generate the
Yeah,
mapping file.
Xilinx Vivado is given for that mapping and all. These what all steps I'm talking about. These all steps are in Xilinx Vivado. If I got time or if I got the opportunity, I just share what all Xilinx steps are given. These are the all steps of Xilinx Vivado tool. Everything is given there: simulation part, implementation, and how bit stream generation. Everything we are doing in that particular Xilinx Vivado tool. And then whenever our final bit stream generated, then we connect it to the board through wires or flash and all. We are connected from our computer, and then we connect to board and test it. If in our testing boards also, I have boards, but if I got the time or opportunity, I just show you. Boards are given. So if our circuitry fully completed, then we connect it, and if it is correct, our circuitry is correct, because in every step we first check whether our circuit is correct or up to date, what all requirements are. Then only we can upload it to the FPGA board. So all these steps are given in Xilinx Vivado 2. This is given to, so that is for FPGA design. So we are using the Xilinx Vivado for this.
Okay, ma'am. Okay, ma'am. So basically, the tool itself will do it for us. Okay. And ma'am, one more thing like this: the CLB inside structure will not be shown. Will there be any document? It will show the complete internal hardware or something in CLBs, IOBs, and all that.
Please
Like
pardon.
generally, like this CLBs, what is inside this? What are the circuits inside this one? They will be showing in some their user guide or something, or like it will be like a closed box for us, like black box for us.
Yeah, this is close box for us, because in chip already it is given in board what we are using now, that is a close box for us. But whatever design, like I am taking Ethernet 10G radar system I am preparing. So in that board, these all small CLBs this is given. But if my application is regarding Ethernet, so I need to deploy my design. That board contain that design. So I need only to complete my task in software in Xilinx Vivado, and then when we connect and if your design is correctly verified, then only it is in board it is deployed. Otherwise, it is not working in our board if we connect. So this is like a black box for us. Yeah. Today, actually, I am showing only introductory part of FPGA. If you want to know, I can show you all full CLB structure, DSB structure, VRAM, how it inside what it is there. I can complete all tasks. If you want further PPT, I just explain everything, each part. Because but today I am just introductory part I am giving, so that's why. Very less, my slides are very less according to me, and I think my speech is very less. So anyone other question? Anyone?
Oh no, ma'am, it's okay. It was fine. So can we drop the meeting? Anyone have any doubt?
Ma'am, one doubt, ma'am. What is the prerequisite of this course, ma'am? Like what we need to know to understand?
For FPGA design, yeah, okay. Some coding part, you should be very fluent in that, like Verilog, VHDL. If you want to move in defense applications, like in defense area, like in DRDO, you want to select or you want to work in DRDO, you need to know VHDL very thoroughly, But now in industrial purpose, if you move to in industry, semiconductor industry, you need to know Verilog, system Verilog, or UVM, OVM also nowadays come. And that UVM, Verilog also similar, but these two languages is in industry purpose, it is very useful, and these two languages are more useful than VHDL. VHDL is older, but in DRDO, in defense, we are using VHDL. Still, we are using VHDL. So in many places, in many industry also, VHDL is still uses, but VHDL is main. Then Verilog, system Verilog. In semiconductor industry, Verilog, system Verilog. If you know Verilog, system Verilog, that is very, very good for you. So and main basic concept is digital electronics. If you are thoroughly good in digital electronics, then you can easily learn Verilog, system Verilog. That is not complex like other Python, TCL languages. So these are the basic, very basic languages, Verilog, system Verilog. You can easily learn. So for FPGA, this initial language, so first of all, like in this step I am showing right now in my slide now. So in first step only we are completed all coding part, and then we move to synthesis. That is another thing. If your code is ready, if your you know your design, how to implement it, then synthesis is a direct process that is given in your tool. So you just need to check by clicking okay, synthesis, this is my net list, all my voltages, currents, everything is come. So now then implementation. First is main is coding part. If you learn coding, if you understand coding, that is well and good. So this is the main thing for FPGA course you want to learn. First is coding part, and before coding, digital electronics thoroughly. If you know digital electronics, like you are master in FPGA verification. That is must and must. So like that.
Okay, ma'am.
Anything else? Yeah.
Okay, then thank you guys. Thank you so much. Thank you, ma'am.
Thank you so much for giving me this opportunity. Thank you. Bye.